going to cover Paxos today, which is a distributed consensus algorithm. And you may have until now developed your intuition that this course is majorly about having logical clocks on distributed systems and then making a consensus, okay, whether it is to select a cluster head or developing some kind of consensus on some task, okay. So today's we will continue about consensus, and today's topic is Paxos, okay. um, Lastly, previously we have covered Hadoop, and in that system lecture we studied about different examples to understand Hadoop and how does it help us in solving distributed problems on a larger scale, and with like approximate performance. It means that performance might not be ideal. That is about time needed to reach or execute some task, but eventually we will have enough resources in distributed system to solve that problem, okay. So one of the many examples were about PageRank, and I last time I gave you this network to solve it about what is the PageRank, okay. So I have solved this with the dumping value of 0.5, and you can like calibrate your answers if they are of similar value, okay. You can also test with 0.85 dumping value, so both are acceptable, okay. So this should be the answer about this problem, okay. Today we will, as told before, we are going to study Paxos, okay. So we will have some definition of Paxos and why we need it, or why we need it in particularly for developing a consensus, okay. How it works, and some detail about Paxos, and after practical case we will have several examples, okay.
So the problem is how to detect and sequence concurrent requests. That's a problem, and we want to go from very hierarchical centralized system to a majority based or parliamentary system, okay. And I'm using the word parliamentary to motivate the algorithm I've been talking about, and hopefully you've been waiting for. It's called Paxos. Paxos is a location in Greece which had a fictional consensus system. And how many of you guys have heard of Leslie Lamport? How many of you have heard of the Turing Award? You know anyone who's got a Turing Award? Fred Brooks. We are in his room. So Leslie Lamport is also a Turing Award winner, a brilliant guy, and like Fred, an extremely good speaker. You know, so he gave a distinguished talk, in fact, at UNC, and I've seen many theory talks, and I think that stood out the most. That was the clearest talk I've seen, and what was interesting was that he just had a slideshow essentially. Every line was a new slide. And I think this might have been in the time when we actually had slides. But I learned a lot from the way he presented things. Okay, so we're going to talk about Paxos. And what you learn from this slide is that Paxos is something that needs simplification. Okay? And yet, so Paxos actually, Lamport wrote he did the first paper. Actually, from what I believe the history is, and I'm not 100% sure, that this algorithm was invented in the late 80s by both Leslie Lamport and Barbara Liskov, who's another Turing Award winner at MIT. And they both came up with it independently. I think I read it somewhere, but I'm not 100% sure. But it was written up in 1998 by Leslie Lamport. And then he wrote this paper saying, he says, look, whenever I go to conferences, theory conferences, people say it's too complex, so let me make things more clear by removing all the Greek symbols and just talking plain English. Okay? So it's the simplest and most obvious of distributed algorithm according to him.
Okay, I hope the system sound was clear. Okay. So it was about to the emphasize on Paxos algorithm and the person behind that. Okay, so that's was the purpose to put that those two slides in this lecture. So Paxos is an algorithm that is used to achieve consensus among distributed set of computers that communicate. Okay, and it was proposed as we already came to know that by Leslie Lamport, and the purpose for and he claims that this is the simplest and most straightforward algorithm to reach consensus. Okay, this was published back in 2001. Okay. So let's take a simple example to understand Paxos. Um, on a abstract level. Let's say that there are four friends and they want to develop a consensus on doing something. Okay, they have nothing in mind particular, but they are coming up with some idea that what they should do after. Okay, so first guy says that let's go to cinema, and the second person says okay, let's go to the cinema, but the third person has a different idea. He says that let's go to dinner, and the fourth person, he says that okay, let's go to the cinema. Okay, so you can see that there are three persons which are aiming at this, going to cinema, and there is a one person who is aiming at going to dinner. Okay, but this is their raw ideas and their proposals that what they want to do, and this guy later changed his mind based on the other opinion that okay, let's go to the dinner. Okay, and then this person also changes his mind and he says that okay, let's go to the dinner. Okay, and this person, the fourth one, he is the only person left with the proposal that he want to go to cinema. Okay, since the majority, okay, 1 2 3, they have decided that they want to go on to the dinner. Okay, so majority wins, then he has to accept it. Okay, accept the proposal, though he wanted to go here, but initially. Okay, but no, he has also reached on the consensus that let's all go to the dinner. Okay, because the purpose is that all should have a consensus. Okay, and the majority wins. So this is the rule in the Paxos algorithm. Okay, consensus is agreeing on one result. Okay, once a majority agrees on a proposal, as in this case, these three guys, after some discussion, and they propose that they want to go to the dinner. So this is a majority. Okay, so that is the consensus, and on that consensus, the fourth guy will also come in and join the majority. The reached consensus can be eventually known to everyone. Okay, the involved parties want to agree on any result, not on their proposals. Okay, though their proposal was to go to cinema, but this is not like a very hard and fast rule that you have to entertain their request. Okay, eventually after some discussion they will reach a consensus, and this is not important or final that all will develop the consensus, but most of the person will develop a consensus, and the rest of the guys, they go with the crowd. Okay, communication channels may be faulty. Okay, that is a message can be lost. So this is possible in distributed systems, and there should be some kind of fault tolerance in that system. Okay. Um, so let's take an example. So you buy a workstation and you install an algorithm and call this a server. Okay. But after some time, the resources reach their peak point, and then you have to increase, for example, RAM or hard disk. Okay, the system is bigger, but again with time, same problem will occur, and you will have to upgrade your system. Okay, and but how what is the limit to go? So this is not like infinitely larger system is not possible. So there eventually will come a point that you have to decide about what is the proper solution. Okay. Okay. So so there is like one system at your premises giving you all the facilities and extensions and scalability is not possible. Okay. So you can either go for replicating the systems. Okay, but one should be the leader. Okay, so you have to select one the leader, and the rest of the guys have replicated database. Okay, to entertain the requests. Or you could have the other option is peer-to-peer schema. Okay, but in peer-to-peer schema, you know that you have to continuously developing consensus on data integrity, that all the peers should have the same data. Okay, in this case there should be one leader, and they should join in to select that leader. Okay, with consensus. So you can see that in either of two system, consensus is required. Okay. So in distributed system, we have this server client system and this peer-to-peer system. But eventually we came to know that in both type of solutions, okay, of this problem, we need to have consensus. So this is the need why we must have a consensus algorithm. Okay. So there are some assumptions for this Paxos algorithm. First is concurrent proposals. Okay, it means that one system can get multiple requests. Okay, concurrently, uh, only if what request should be entertained first, and what should be entertained later. So we will understand with the detail of Paxos algorithm. Okay. So we know that the first request or proposal and second proposal, whatever gets the majority consensus, okay, they will be entertained, and the rest will be put in the queue until they have reached some consensus. Okay. Validity: the chosen value that is agreed upon must be one of the proposed values. The servers can not just choose a random number. Okay, so value, for example, you want to update your storage. You have a banking system, and the value of the transaction should be updated, and there should be some log. Okay, so this could not be like some kind of a random value. If this is some pseudo number, the new number will be like different as compared to the previous number. For example, it should be incremented, for example, by 1. Okay, so that we know the validity of proposals or request. Okay, so we can request or proposal in this case are synonymous, and in this lecture we will use a proposal, for example. Okay, let's go back to the example that he want to propose. Okay, let's go to the cinema. This is proposal 1, and this is proposal 2, 3, and 4. Okay, so requests are proposals in this lecture. Majority rules. Okay, as given in the very same example earlier, that if like a majority of servers agree on one of the proposed value, okay, we have a consensus on that value. What does it means that this is consensus and the remaining server had to agree on that value, okay. This this also implies that a majority of servers need to be functioning for the algorithm to run. To survive M failures, we will need to have two M plus one servers, okay, systems. So this is for failure that we earlier kind of touched that it should be handling the failures, okay. For that, the thumb rule is that if there are possibility of M failure, we need to have these many systems, okay. Unicast communication is point to point. There is no mechanism to multicast a message automatically to the set of Paxos servers, okay. So in this algorithm we are assuming that the system is point to point, okay. So announcements are made like once consensus is reached, result can be made known to everyone, okay. Uh, in the very same example that when these three guys reach on a consensus for a dinner, and this guy was communicated somehow with some mechanism that these three guys are like wanting to go to dinner, and then after he knows the result of them, and then he need to decide have go with the majority, okay, which is going for dinner. So once consensus is reached, the result can be made known to everyone. Okay. There are these are a few basics of Paxos algorithm, and which are giving you the crust of that algorithm. That what are the components and how does they work? Okay, and what are their roles? So a Paxos node can be in one of these roles, proposers, okay, which give a proposal and acceptors, and then there are learners, okay. Can you highlight that what one of those node, one is the acceptor, okay. Can you highlight from this example that these three are acceptors, okay. They finally reach a majority consensus that they want to go to the dinner, okay. So which guy is the learner? Yes, anyone in the class? Go ahead, please participate in this discussion. Okay, so let me explain it. That this guy is an acceptor, okay. The learner, he had learned from the other responses from other fellows that okay, let's go for dinner, okay. So let's go back to the business, which is over here, slide number 18. Okay, this is not a very large lecture. Maybe 18 slides are covered and just 17 are left, okay, or maybe 16. So please pay attention. This is although the simple algorithm, but you need to understand intuitively with the help of examples, okay. Um, Paxos nodes can take multiple roles, even all of them, okay. This is a possibility. Um, Paxos node must have know already that how many acceptors a majority is, okay. So it should define the number. For example, there are 4 persons and 3 is the magic number for majority, okay. Or if there are 3, 2 can be the majority majority number, okay. So 2 will always overlap, okay. At least one node. So there, if there are only 2 nodes, then one could be the majority, okay. So this is a number that could be variable. Must be persistent, okay. they cannot forget what they accepted. Okay, so you can see that they have record of previous their proposals, and then they modified it. So they have a kind of history or log of their previous acceptances or of about the proposal. Okay. Um, uh, Apexes run aim at reaching a single consensus. Okay, so there cannot be, for one proposal there cannot be more than one consensus. Okay, so consensus is about one proposal. Okay, although there could be several proposals, but they have to agree on a single proposal. Okay, once a consensus is reached, it cannot progress to another consensus. Okay, so as we studied in the example that the four guys they reach on a consensus to go for dinner after afternoon, so they cannot change their mind. Okay, they have decided and they go for dinner. Okay, in order to reach another consensus, a different Paxos run must be made. Okay, maybe on other day they want to go for another they want to have another activity, they must develop a new consensus. Okay, so these are the basics. We have in distributed consensus algorithm. What we need to have, we have an environment of multiple systems. Okay, which in this case are nodes. They are connected by some kind of networking, and so initially one of those nodes can concurrently propose a value. Okay, for example, in to perform an operation on a server, select a coordinator, add a tag, add to a log, whatever log. For example, they want to update the database with some transaction, which is they want to uh, add $10 in their account. Okay, so that account is not on a single server, and it usually have multiple databases that are replicated. Okay, so in that case, what we do is um, they will first reach a consensus on a value. Okay, and then this value will be communicated to all the server which have that user database. Okay, bank database, and then uh, based on that log we will know that okay, first database 1 was updated, and that communication will be communicated to other database servers like database 2, 3, and 4. And then after first transaction is done, same is replicated in the other databases, so that there is no conflict in the business transaction. Multiple proposals are proposed, and single acceptor are there. Okay, what if the acceptor crashes? Okay, so we will in that case we need to have like multiple replicated servers. Okay, fault tolerance, multiple acceptors. So in order one node is failed, and that in that case we have to make this possibility that there are multiple acceptors. Okay, well, um, in Paxos, as communicated earlier, there are three entities. No need to go into the details. Proposers, acceptors, and learners. Okay, learners announce the outcome. Okay, which has to be agreed by left over parties, and then we have all the parties agreed on a single value. Okay, values in this case was somebody can propose to go for dinner, and one somebody can propose to go for cinema. Okay, these are the proposal values. Okay, from clients, and try to convince acceptors to accept their proposed values. Okay, these clients will have will do their effort to get their proposal agreed, but there is no guaranteed, okay, but majority will be developed, and consensus on based on that majority will be implemented. Acceptors accept certain proposed values from a proposal, okay. So there were like two values proposed, and the acceptors can accept either of these values, okay. If something else was accepted, a response from an acceptor represent a vote for particular proposal, okay. So remember again, we want to go from monarchy system to a vote-based parliamentary system. So we know that majority rules. Okay. So in same idea is borrowed from there and implemented over here. So you can heard about proposals and votes and majority. So this is the vibrations from that basic abstract idea. Okay. In practice, a single node may run proposer, acceptors, and learner. Okay, rules. It is common for Paxos to coexist with the service that required consensus. Okay, so if you want to implement this algorithm on a distributed system, for example, distributed storage, uh, so this is possible because it is based on consensus. Okay, so it can work on these systems on a set of replicated servers, which with the each server taking on all three roles rather than using separate servers. Okay, so this is the benefit for the sake of discussing the protocol. However, we consider these independent entities. Okay, anyways. Paxos protocol have two phases. First phase is a proposer asks all working acceptors whether anyone already received a proposal. If the answer is no, propose a value. Okay, so you have to propose a value to each participant. Okay, in phase 2, if the majority, as we saw in the example, is agreed to a proposed value, then that is our consensus. Okay, so this is very simple two phases algorithm. Okay. So let's go into the further detail. When in coming slides there are only interesting examples, so this will be very useful. Okay, please bear with me and go through this remaining explanation of Paxos algorithm. When a proposer receives a client request to reach consensus on a value, the proposer must create a proposal number. Okay, this so why we need different proposal numbers? Because we want to identify different proposals with the unique number. Okay, and so if we have received proposal 1, then there will be proposal with number 2 value, and 3 and 4 and so on. Okay, so these are called the proposal IDs. So it must be unique, as we can imagine. No two proposal can come up with the same number. An easy way of doing this is to use a global process identifier for the least significant bits of the number. So this is one of the techniques to have a unique number to identify the proposals. Okay. For example, instead of ID 12, node 3 will generate ID 12.3. Okay, so this is to identify proposal 1 with different unique number, which is zero point 0.3, and node 2 will generate 12.2. Okay, it must be bigger than any previously used identifiers. Okay. For example, 12 should be bigger than 10, which was previously proposed. It must be okay. A proposer may use an incrementing counter or use a nanosecond level timestamp to achieve this. If the number is bigger than one previously used, the proposal will find out by having its proposal rejected and will have to try again. Okay, so it can identify that if the request is new or it is older. Okay, so let's proceed and okay, let's go to the more detail about phase number 1 and 2. Okay, so these are the phase number 1 and 2. Okay, proposer receives a consensus request for a value from a client, and then it creates a unique proposal number, which is ID, and sends a proposed ID message to at least majority of acceptors. Each acceptors that receive the prepare message looks at the ID in the message, okay, and decides. What it need to decide is this ID bigger than any round? Because if the ID is smaller than the current ID, it means that the request was proposal was already floated in the network. Okay, so it doesn't need that. It only need to entertain new request. Okay, that's why it will compare the ID if it is updated or greater than previous IDs. If so, it means if yes, store the ID and define maximum ID. Okay, let's say if that ID was 12 and it will define max ID, for example, 12.2 or 12.3. Respond with the promise. Okay, so they are promising that okay, whatever the proposal was, and then they can promise, or if the ID was lower or request is older, so do not respond. Okay, so this is in order to avoid many messages in the network. So we have to accept only the messages with the fresh ID. If the proposer received the promise so here they have sent the promise response. Okay, uh, from a majority of acceptors, it knows that majority of them are willing to participate in this proposal. So what was the proposal? Either going to dinner or either going to cinema. The proposer can no propose with the getting consensus. Okay, each of these acceptors made a promise that no other proposal with a smaller value can make it to the consensus. Okay, so the phase second is propose and accept. Okay, first phase was prepare and promise. So here we got the promises. Okay, here over here. And then how about accepting the proposals? Okay, if proposer receives a promise message from the majority of the acceptors, it now has to tell the acceptors to accept that proposal. Okay, if not, it has to start over with another round of Paxos. Okay, if this phase of in this phase of protocol, the proposer tells all the acceptors that which are alive, okay, which are up and running, what value to accept. For example, either they should go for, this is about remaining node. Okay, remember about the guy number 1 who was aiming at going to cinema, and later the protocol should inform that guy to that no, you have to accept that proposal. Okay, so in like pseudocode, if the ID uh, the largest I have seen so far, the maximum ID is this. If yes, reply with accept message. Okay, so the nodes either which have already promised or which have not accepted, they all have to accept. Okay, and send the accept value and ID to all the learners. Okay, if no, do not respond. and send a fail message that consensus is not reached. Okay. Um, this is the summary. Okay. Accept message can be sent back to the proposer as well as learner, so they can propagate the value to whatever whenever its action is needed. Okay. So this is again the summary. This is that we have already talked about. Basically, in phase 1A, we need to prepare a message in which we select a number which is n and send the prepare request prepare n to our quorum to accept. Okay, to acceptors. Then we in the phase 2A, we talk about accept. Okay, if the proposer received promise response from a quorum, okay, uh, send and accept n and w. Okay, where w is the value of the highest number proposal among the promise. So you can see that three guys agreed on some proposal, and this is the number or any value if no promises are made to this proposal. Okay, and in phase B, where we have a promise, and if n is greater than number of any previously promises or acceptors. Okay, so it means that if on proposal n, okay, there could be different proposal. For example, in initial example, it was going to cinema or dinner. Okay, so for dinner, if there are, for example, one, and for another proposal there are three, so the greater number is three. Okay, so promise is made by three number of participants, their response, and then on acceptor, they all accept. This is the majority. Okay, greater than equal to number of any previous promises. So finally, majority wins, and they accept the proposal, and all uh, develop consensus on single value. So let's go through some examples, and we will finish this lecture. So you can see that if in this example there are two proposers, and there are three acceptors, and there is a learner. Okay, so a learner, like they all have to agree on a single value. Here you can see that proposer propose to these nodes 1, 2, and 3 some idea or value, and similarly by proposer 2, he also propagate his proposal, and finally they learn about you can see that if these two guys accepted his proposal, the learner will know. Okay, learner will communicate to this and this guy, and finally this also has to agree on the majority. Okay, so we can like imagine the same example over here, and similarly over here, let's say there again there are proposer A and B, and there are three acceptors, like X, Y, and Z, and there is a learner. Okay, and this proposer proposed some value. For example, here it has some idea that he proposed to X, Y, and Z. Okay, and finally these three, their acceptance or promise is conveyed to the learner, and learner communicate back to all these nodes, and finally they agreed upon a single proposal. Okay, since you can see here they have to decide. Okay, so 50 is the the proposal they agreed upon this. Similarly, let's take understand this algorithm by another example. Here you can see that this proposer 1 has sent its proposal to the three acceptors. Okay, and in reply this acceptor 1 has promised to with same ID 5. Okay, and after some time proposer 2 also propagates its interest or uh, its proposal to the three of these nodes. And here you can see that before after this proposal, uh, this acceptor 2 also agreed with the proposal or value proposed by this. Okay, so at this point we do not need to consider this because we have already reached the consensus. Okay, even though we don't know the answer from acceptor 3, but majority is achieved, and through learner we will propagate this value 5, and it has also need to agree with this. Okay, so if a majority acceptor promises to ignore anything lower than ID, okay, so this is the lower ID, so it should be ignored. No ID lower than that ID can make it through. Okay, so this is an example. So take the similar kind of example for if there will be a contention. Okay, you can see that this proposal 1 prepared message 5 or proposal 5 and sent it to here. And you can see that the two nodes promises promised over here, and over here they also have two promises, although this will be so this will be considered. Okay, because priority. And then again this request is sent, and this is ignored and ignored, and after some time new proposal came, and uh, uh, they agreed on promise 3, promise 7. Okay, so we can clearly see that there could be contention in this case. Okay, in order to avoid from a contention coming up with several proposals. Okay, so here is proposal number 5 and 6. Okay, 7, and here we have a proposal 6 and 8. So there is a contention. Okay, so you can see the here also majority applies, and here also applies. So this is a contention, so which proposals to accept. So, or how to solve this contention? So we can have several solution that could be applied over here. For example, exponential weight. We can apply that. We cannot accept a new request until we have reached a consensus on the first proposal. Okay, so this can be the solution. So this is a bank example that we have already studied in different lectures. So here we can see that um, we have three replicas, A, B, and C. Okay, and what we need to do is to maintain their log. That position 0, what was the value? Position 1, 2, 3. Similarly over here. Okay, so 1, 2, 3. There is log values. Okay, so here we do not have log 3. For example, in Paxos algorithm, you may imagine that these are the two nodes which have reached consensus, and this is the majority. Okay, a similar kind of update will be made over, and it has to do that update over here. Okay, so this value will be updated over here. So imagine that you want to withdraw $30. Okay, over here. Okay, in your local bank, and of course this transaction will be done, but this should be updated upon other replicated servers. Okay, so in this case these servers are Paxos nodes. So first it will communicate to this node that Paxos run user Lewis log position 3. Okay, so this is a log position 3. This position is communicated over here, and this similar is communicated over here. So you can see that we can solve the bank transaction issue using Paxos algorithm. Okay.